The next thing I want to talk about is what it means to be a solution to a linear system. And most students are probably already familiar with this idea in two dimensions. So let's talk. First of all, definition. A solution to a linear system. System in n unknowns is any what we call n tuple x1 x2 x3 dot 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 x of n such that all equations in the linear system are satisfied simultaneously. So let's talk about what that means. First of all, what does this term mean? What's an n-tuple, dude? Sounds like a weird pastry or something. Let's talk about what that means. So in 2D, you're used to ordered pairs of the form xy. So this would be an ordered pair. And for our previous example, 5x minus 2y is equal to 2, and negative x plus 2y is equal to 6. If we simply look at the ordered pair, 2, 4, maybe. 2, 4. What we're going to see is that 2, 4 is what we call a solution to the differential equation because, easy with the marker there. 5 times the x value 2 minus 2 times the x value 4 is 10 minus 8, which is 2, and it satisfies that equation. However, it also satisfies the second equation simultaneously. A negative 2 plus 2 times 4 is equal to negative 2 plus 8, which is equal to 6, and it satisfies them both. And so, I'm not sure why I chose that color. 2 comma 4 is a solution to the above system. We also want to note things like this. 0 comma 3 satisfies equation 2. That is to say, negative 0 plus 2 times 3. That's equal to 6. But 5 times 0 minus 2 times 3 is equal to negative 6, which is not equal to. And 0, 3 does not satisfy equation 1. And so 0 comma 3 is not a solution. So that's analytically, that's by the numbers there. The other thing I want to talk about is how many solutions are possible. So up here I said a solution to a linear system in n unknowns is any n tuple. So what is an n tuple? Let's go back to that. For a system in 3 variables, like 2x1 plus 3x2 minus 5x1 is equal to 0, and x1 minus x2 plus 3x3 equals 5. A solution would be an ordered triple, x1, x2, x3. Ordered triple. Or more classically speaking, probably an XYZ is what most of you are used to seeing. An ordered triple. And then after that, in a system with 4 variables, it's an ordered quadruple. And with 5 variables, it's an ordered quintuple, and that's where the tuple, the tuple, is coming from. And so instead of saying quadruple or hextuple, they just say it's an n-tuple. So that's where that term comes from. How many solutions are possible? Let's talk about another definition. A linear system has what's called a solution set. This is the collection of all possible solutions to a given linear system. Now, in order to talk about how many there are, we really have to have a conversation about dimension. But this conversation is probably one that you've been having since junior high, when you were first introduced to graphing lines. So, how many solutions are possible? Well, in 2 dimensions, our linear equations are lines. So if I have a system of 2 equations, and I draw a couple of lines here. Here's one line. Here's another one. Something like that. There we go. Line 1 and line 2. These 2 intersect at a single point. This is xy, the intersection, or I guess more appropriately, x1, x2, if you want to think about it that way, or x1, comma x2. This system has one solution. So there's only ever going to be one answer for a system like this. But as far as other linear systems go, maybe you can think of a different way that these lines can interact. Let's see. Here's a blue line. Let's do a red line. Try to make it look good here. Let's screw that up. Let me start over. Here's the red line. We'll do the blue line. And I've tried to draw these so that they're parallel. And so in this instance, these lines are parallel, and there is no intersection, which means that there is no solution to the system. There is one more scenario, though. Here's my red line, and this is going to look a little bit weird. I'll do this in blue. Let's see. I'll do it in the highlighter here. No, it's too small. Bigger highlighter. And so I've tried to draw them here so that they're the same line, right? These lines are the same and intersect at all points they have in common. And so in this system, there are infinitely many solutions. And it turns out for linear systems, those are the 3 main possibilities you're ever going to have. That's actually how you count in a linear system. It goes like this: 0, 1, infinity. So, playing hide and go seek in linear equation math, you get to count really fast. 0, 1, infinity. Here I come. Those are our 3 main possibilities. And in the first one, And the third one, there actually are solutions. This is called a consistent system. As is this. This is a consistent system. This is an inconsistent system. And that refers to simply whether or not it has a solution. The system has a solution. So, definition. If a linear system has at least one solution. Now, for us, that means one or infinitely many solutions. Then the system is consistent. And that's the term I'm trying to define for you here. Oops, I need to readjust the size of my highlighter. The system is consistent. There we go. If a linear system has no solution, it is inconsistent. So, what will that look like, right? That's something we're going to see a little bit more in the next section. But for those of you that have a keen eye for this kind of thing, 5x minus 2y is equal to 2, and negative x plus 2y is equal to 6. That is a consistent system. How can you tell by looking at it? Well, if you were to solve for y, the fact that these two equations have different slopes, slope 1 does not equal slope 2, then they're going to have to intersect. Here, slope 1 and slope 2 are equal, that they're parallel. That's how I know that they're parallel. But in situation number 3, the lines are also parallel. M1 equals M2. But y-intercept 1 also equals y-intercept 2. And here, intercept 1 and intercept 2 are not equal to one another. So there's two different versions of parallel, and that's where it gets a little bit dicey. So be careful about that. But right now, we just want to be able to classify the system as having no solution or at least one solution, consistent or inconsistent, not respectively. I think I said those backwards. So if it's got at least one solution, it's consistent. If it has no solution, it is inconsistent. Now, as we go up in dimension, the geometry changes a little bit. In 3D, when you talk about AX plus BY plus CZ equals D, or A11 X1 plus A12 X2 plus A13 X3 equals B1, these are linear equations in 3 variables, and geometrically speaking, they're not lines. These are planes, and they can interact in a few ways that lines can't. And I'm going to do my best to be an artist here, so bear with me, folks. I'm going to draw some planes. Let's see. Without being too technical. There's my first plane. And I can have a second plane here. And I'm trying to draw them so that they are, in fact, parallel to one another. So, parallel planes. There is no intersection. So that system would have no solution. You can actually have, if you just have two planes, let's see if I can draw this one. Yeah. That could have been worse. Here's two planes. And they're going to intersect along this common line here. So this is like a revolving door. Well, yeah, and this is its axis of rotation, if you will. So change the color back here. Two planes can intersect along a line, which means that they have an infinite number of intersection points, which will translate to an infinite number of solutions. There's another way that you could have an infinite number of solutions here. This one's going to be a little bit harder for me to draw. Let's see. Here's my plane. And I'm going to draw this other one that lies right inside of it. So this is one plane, quote unquote, inside another. I'm not sure if that's the best term, but these are parallel, and they coincide with each other. This is also infinitely many solutions. There are other no solutions too I could have drawn for you guys. Let's see, with more and more planes. But let's move on here. It's going to be hard for me to draw. Bear with me, folks. So, what am I forgetting here? I left something out. Maybe this guy. So, that drawing is getting better. Any two planes intersect in multiple spots, but this is one single location that all three planes have in common. So this is three planes intersecting at one point. So even though there's multiple different scenarios here, we still have no solution. Can't spell. No solution. One solution. Or infinitely many solutions. So we're going to see that as we go up in higher and higher dimension. Now, I can't really draw anything for you in 4 dimensions, but the analogy holds as we go in higher and higher dimension here. So one thing that we're going to be asked to do in the future is classify these as being either inconsistent or consistent. Okay.